Let's get started. So first of all, let us introduce ourselves. So we are GraalPy developers. GraalPy is an alternative Java-based implementation of Python that aims to be compatible, fully compatible with Python, and it has a JIT compiler from the very beginning. It was designed with JIT compilation in mind. So we've been working on JIT compiling Python code for more than 5 years now. We don't work only on JIT compilation with GraalPython. Big part of our daily job is to work on the GraalPy compatibility with the Python ecosystem, with the native extensions, with the Python packages. And we've also contributed and joined the HPy project, which is an alternative to the CPython C API, which is supposed to be better C API, and we will soon see why we think it's better. Let me use this occasion to also shout out to the community members that have been helping us pushing the GraalPy compatibility with the ecosystem forward. We believe that a viable Python runtime alternative can future-proof the ecosystem. And because like many of the problems that are problems for many of the things that are problems for GraalPy now might be soon problems for CPython. Back to us, at last but not least, we work on integration of GraalPy with the Java ecosystem. That's because since GraalPy is running on Java, it's a natural thing to do. We have plugins for the most popular Java build tools that let you integrate a Python package installation into the Java build. We have APIs to seamless and efficient communication between Java and Python. And not only seamless, but from the API perspective, but also from the performance perspective, because the two languages in the case of GraalPy are running on the same virtual machine on the Java virtual machine. So long story short, with all that, you can embed and run Python from within Java applications, or you can use Java libraries from Python with GraalPy. So now, that's been enough for our introduction and GraalPy introduction. Let's take a look at the plan for our talk. So first of all, this is not going to be JIT compiler shootout or trash talk. The thing is that JIT compilation, as we might have seen in the previous two talks, is a subtle topic, and the idea is to give guidance, understanding, and you have to make your own opinions and measurements and see what works and doesn't work for you, because as with everything in life, there's no one size fits all. We will use one running example to illustrate why it's hard to compile Python and what is the general approach to compile Python. We will explain inner workings of some of the selected just-in-time compilers. And then we will talk about obstacles for JIT compilation as we see them now, and what we can do about them, and then about interactions with, of JIT compilation with free threading. So as a first step, we should define what we mean by compilation so that we actually know what we're talking about, right? And we want to put it in contrast with interpretation. So both of these approaches usually start with converting Python code into some sort of bytecode, which is a flattened, more memory efficient representation of the same thing. And the instructions in the bytecode are sort of imaginary instructions for a virtual imaginary machine. The idea is that they are better suited for interpretation and compilation. An interpreter is a program that reads those instructions one by one and executes them as they go. It doesn't generate any new machine code at runtime, and it executes each of those instructions in kind of isolation without the context of the surrounding instructions. On the other hand, compiler transforms a fixed, concrete sequence of bytecodes into a machine code that, when executed, performs those bytecodes. But that machine code is specific to this one specific sequence of bytecodes. And the goal of JIT compilation or compilation in general should be faster execution of the bytecodes. And this is the example that we will be using. It might look a little bit familiar to the example that was used in the previous presentation, and that's not a coincidence. So it's a leg difference sum average algorithm. We basically loop over a list with integers in it. For each element, we take the element and the absolute value of the difference between the current element and the element a few positions earlier. If the difference is small, we just add it to the total. If it's larger, somehow, defined by this isSmallDiff function, then we penalize it a bit more. So now let's focus on the highlighted operation, and let's talk about why it's hard to JIT compile Python. Here we have a subtraction of two values. And the question is, can we just compile this like a C compiler would into a machine native operation that subtracts two 64-bit integers? And if you've been to the previous presentation, you know the answer already. No, we can't. The first issue is that the subtraction can underflow. And Python supports arbitrary large integers, right? So we cannot just underflow back. And we actually need to create a large or big integer for this. Another issue is that the numbers are boxed in some structures that are kind of generic, represented generic Python object. So we need to extract them. Another issue is that they don't have to be integers, they could be doubles. And even more, they could be arbitrary objects that define the dunder sub or dunder r sub methods. So we need to look up those methods and call them. So this is all complicated and very far from like a single machine instruction that subtracts two integers. And that single instruction that subtracts two integers, that's what we are aiming for. That's why we are doing JIT compilation. Not that we compile the whole generic algorithm, because that would be quite the same as the interpreter. Now another example of function calls, something as simple as a function call, cannot be compiled to what a C compiler would produce, because the function can be redefined. Right, so we don't know the target function. We need to use some indirection for the call. And that's not that bad. The major consequence is that we cannot inline the function. And inlining in compilers is one of the most important optimizations. And another example, just to illustrate this, why it's hard and complex to compile Python, something as simple as reading an attribute under the hood is really this complex algorithm, and we didn't even include all the steps in here. So what shall we do about this? One possibility, we just give up, and we say, like, let's re-implement the performance-sensitive parts of your program in a different language. But we are at the biggest European Python conference, so hopefully I don't need to convince you that Python is a good language, and we probably want to use Python over C++. Another option is to restrict the language. We've seen that possibility in the first presentation today, or in this track. And that's a viable possibility, but the issue is that like even benign restriction in the language might have huge consequences for real-world code. Real-world code usually has lots of dependencies and transitive dependencies, and even small change could be problematic. Another possibility, if we want to keep the comparability, then, and we still want to compile the code, then we need to use something that we call runtime specialization. And that's the generic idea behind all the JIT compilers that we're going to present today, and probably most of the JIT compilers for dynamic languages in general. The issue with dynamic languages is that we cannot, ahead of time, before running the code, we cannot statically analyze it to find out all the types and all this other information that we need to efficiently compile the code. So what we do instead, we run the code. We run it for a while, we observe it while it's running, and we use those observations about the types and other things to produce the efficient machine code. Why do we think it's possible? See JavaScript, which used to be very slow interpreted language, and over the time it evolved to this language that has advanced virtual machines like SpiderMonkey or V8. They are quite fast, and there are some situations where people want to use native code from JavaScript, but not as much as in Python, I would say. So with this in mind, let's take a look at the example again. with this subtraction, let's say we've run this for 100 times, and 100 times we've seen 2 integers being subtracted. The question is, can we just now compile this into a single CPU instruction that's subtracting integers? The answer is not really, because if we run this for 100 times, the values might not be integers, right? So we've made some observations, we're making some assumptions, and we need to check those assumptions before we execute the optimized code. If the assumptions don't hold anymore, or the observation don't hold anymore, what we do is that we jump out of the compiled code, which is usually called the optimization. And the thing with jumping out of the compiled code is that we don't need to compile the whole generic algorithm into the machine code, which makes it shorter. That's a good thing. And one other, even more important thing is that since this jump out of compiled code never returns back, the compiler, when it's optimizing the code, doesn't need to take this possibility that caused the jump out of the compiled code. It doesn't need to take it into account. So if we do this subtraction here, and it's successful, it doesn't de-optimize, then in the subsequent operation, we can assume that the variable TMP is already a 64-bit integer, and we don't need to check it again. Now this optimized absolute value computation is also de-optimizing if the value underflows. But then after that, we do this comparison with 5, and that doesn't need to check even, it doesn't need to check anything, and that would produce really can produce really the code that's equivalent to what a C compiler would produce for this piece of code. Now, let's take a look at the selected JIT compilers, right? So we've benchmarked this example quick and simple way using the timeit module. Just a side note, if you do benchmark JIT compilers, and if you want to benchmark specifically JIT compilation or the performance of the JIT compiled code, then make sure that you've given the JIT compiler enough time to actually warm up, collect the observations, do the JIT compilation, which also might take some time, and then measure the JIT compiled code, not what happened before, if what you want to measure is the JIT compiler performance. So here we can see how we and how you can install the various runtimes that we've benchmarked, and we can see the results where I think they kind of align what we saw in the previous presentation, that the JIT compiler on CPython is slightly faster than the interpreter, and PyPy and GraalPy are significantly more faster, and we will shed light on why that's so, why we see those results in the next section, where we will talk about the individual JIT compilers.
Yeah, so before we dig into the individual JIT compilers, let's just establish some categories of JITs. One big category is a method JIT, where the main unit of compilation is a method, or sometimes it can be a loop, and it would compile all the possible code paths that happen in that method. But in contrast, a tracing JIT would compile a loop. The main unit of compilation is a loop, and it would compile just a single code path. The way it works is that when the loop would become hot enough to be considered for compilation, it would switch to a different mode of execution that captures the trace, captures all the bytecodes that were executed, and then just those are compiled. That represent just a single code path, and in that trace there would be no control flow. All the ifs and other jumps that were in the code would be replaced by just guards, and if that code path changes at runtime, if you then run the compiled code and it takes a different path, if that was false in a trace suddenly becomes true, it would have to jump out of the compiled codes. And the advantage of tracing JITs is that they are very simple and they are very performant in terms of the actual compilation performance. It doesn't take a lot to produce this trace, and they don't have much overhead for profiling before it gets to the compilation, whereas method JITs can be very complex to implement, hard to maintain, and can be very, very heavy. They can take a lot to compile. But the disadvantage of tracing JITs is that if you have code that often takes different code paths, then it might not compile so well. So the performance of tracing JITs is not so consistent. So method JITs tend to be more powerful in general. So let's look at concrete examples. GraalPy. In GraalPy, our secret is that we don't actually write a JIT for Python. What we have instead is that we have a Python interpreter that's written in Java with some special annotations, and then we have the Graal compiler that uses partial evaluation to compile this Java code of our interpreter, inserting the runtime values from the program to actually create the machine code that represents the running Python code. So this generic way also enables Graal to support multiple languages with just a single compiler. There's also an implementation of JavaScript, Ruby, Wasm, and they all use the same just-in-time compiler. And GraalPy is method-based. In the interpreter, we collect a lot of profiling information about which branches were taken, with what frequency, how many times some functions were called. We observe, like when you're accessing attributes, we create inline caches and observe the cache hits there. We, of course, observe the types, and then when the threshold for a method to be compiled is reached, the JIT compiles it using this profiling information. And our intermediate representation is a graph with nodes that represent some operations, and then there's edges between them for control flow and different edges representing the flow of data. This approach is called sea of nodes sometimes. So the graphs are nice to visualize, so I can later show some examples. And we do a lot of optimizations there. Of course, inline caching, that's what you would expect. We support working directly with integers that are not boxed in any objects. An interesting optimization is list storage strategies, that when you create a Python list and you're appending only integers, we're able to just allocate an array of integers without the overhead of having them boxed into some PyLong object like they would be in CPython, so it's kind of like a NumPy array. And also there's partial escape analysis that lets us get rid of allocations when you create an object and you only use it in that method and it dies at the end. We don't even have to create it. We can just represent the fields directly in the machine registers if it's something small. And a lot of loop optimizations and mild vectorization, but the trade-off is that of course it's slower to compile. So if you have some short running script, it probably will not pay off because the time spent compiling will not be, it will be longer than the actual runtime of the program. So let's look just at some example. It's the same function we've seen before. I highlighted a piece of code that's shown on the graph. You don't really have to understand the graph, but there are just some parts that I would like to highlight. You can see that there are integers and it's doing operations directly on integers. It's checking for overflows, and there are guards for that would jump out of the compiled code, that would de-optimize this compiled code, and you can see that the whole control flow is there, that it's branching with the if. So another very well-known JIT compiler is PyPy. PyPy is written in EuroPython, which is a subset of Python with some type information, and it can be statically analyzed. And they have a JIT compiler that doesn't actually trace the running Python program, but instead it traces the EuroPython code of their interpreter. So it's kind of like GraalPy, that it's generic. It can work for multiple languages than just Python, and there were some experimental implementations of other languages that are built on EuroPython. And so the JIT compiler is a tracing JIT, so everything that I said about tracing applies here. It also implements a lot of optimizations. Inlining kind of is a natural consequence of tracing, because you're just, when you're executing, you just step into that function, and it just happens. Escape analysis is also easy to do when you're tracing, so PyPy just does this. And it also supports working with like unboxed integers and doubles, and has storage strategies just like GraalPy does. So let's look again at some example. You don't really have to understand the instructions, but just to illustrate, you can see part of the trace, and you can also notice that the isSmallDiff function was completely inlined, and you don't even see any check that it's still the function that it was at the beginning, because in Python it can theoretically change in the middle. But PyPy, when it's compiling, it first peels the first loop iteration, so it separately compiles the first iteration and then the subsequent one. So this check already happened in the first iteration, and it doesn't have to recheck it again. So the resulting code of that call is really just the integer comparison and then a guard that it was false, and if at runtime it would be true, it would have to jump back to the interpreter. And in this example, this really can happen. So this is exactly an example of code that might not work so well on PyPy, especially if you're unlucky that at the point when it was tracing, it would hit the code path that was less likely, because it doesn't actually track the branch probabilities. And also CPython has a JIT. You probably went to the previous talk, so I guess I don't need to go into much depth about it. It's technically not a tracing JIT by the strict definition, but it kind of quacks like a tracing JIT, and all that we said about tracing JIT really applies to it as well. So just to summarize, they have a specializing interpreter that collects some profiling information and specializes instructions on specific types, and when some loop becomes hot, they create a trace of the bytecode and translate it into their intermediate representation. That's micro operations, and those are then optimized and then compiled using the copy and patch technique. And it doesn't do that many optimizations yet. If we look at an example here, there's some highlighted stuff, but what I want you to notice is that this whole huge piece of micro ops that's on this slide is equivalent to those two operations that were highlighted in the PyPy example. Like here, CPython doesn't really optimize away, even though it inlines the call to the function, it doesn't optimize away creating the frame and doing all the checks in every loop iteration. It also doesn't unbox the integers, even though the operations are specialized on integers, they still work on Pylong objects with their ref counts and everything. And again, it has the same guard as PyPy did. And so, like, you're probably now convinced, based on all the talks that were there already, that JITs are not a magic go faster machine, but there are some things that can hinder them from working well. One of that is native extensions, and at first, like, native extension call is completely opaque. We don't know what it does, so it's like an optimization barrier. We cannot inline it, and we have to kind of invalidate all the assumptions about the state that could have changed in the meantime. And the second thing is that the C API of CPython wasn't really designed with these optimizations in mind. So there are things like borrowed references that break our storage strategies, because when you get a borrowed reference from a list that was just a list of integers, we have to box all those integers to make sure we track still the ref count and stuff. So CPython is making this a bit more difficult. You can see it in this example. We're calling the same function as before, but before we do that, we just took a sum of the input data of the input list, and it didn't modify it or anything, but just because it observed the borrowed references, it suddenly got way slower. You can see that now the GraalPy performance is getting closer to the CPython performance. It's way worse than before. It's still a bit faster, but not that much anymore. And if we ended up using NumPy even more to actually implement that example function, now we will see that the performance of GraalPy and CPython with the JIT is basically the same. And you can also see that the sort of naive version that didn't use NumPy but was just a bare loop actually performed better on GraalPy, much better. So in this case, even though NumPy is supposedly meant to make things faster, still, because it cannot do optimizations across these calls, it can still come up slower than just a loop. And another thing that might hinder optimization is threading. In this example, you can see that it would be very enticing for a JIT compiler to move the read of this lag variable, it's a global variable. You can see that it's always 3, so it could be enticing to move it before the loop, to just read it once, and then in the loop just keep using that value, because global reads are expensive. And if there's another thread that modifies the value of the global variable, if we optimized it the way I said, it wouldn't be observed. So now it's a question like what the semantics actually should be here, and it's something that CPython doesn't really exactly define. I think people just rely on the implementation. So in CPython it would be read every loop, so we kind of have to do it too if we want to be compatible. And in this example, we would use a global variable for signaling another thread to terminate, but if the JIT would move it out of the loop, it would run forever. So, and also even if the JIT is not moving the reads around, the CPU is still allowed to do reorders of variable reads. So what can we do about it? Well, what can you do about it as a user is to use proper synchronization primitives to they are designed for this purpose, so they make sure that they would work properly even in presence of such optimizations. And so in conclusion, in summary, like if you're asking yourself, like if you would benefit from using a JIT at all, you have to ask yourself, like, is your program just something very short running, one-off script? Then it probably doesn't really make sense. Like you might not benefit because things wouldn't get hot or wouldn't have time to compile. If it does a lot of calls to native extensions, then also not really yet. But if it runs a lot of pure Python code for a long time, then you might benefit sometimes a lot. And what are the roadblocks for JIT compilation? One is the current CAPI, and we would like to ask you as a community, like we can improve this. CPython is already doing some improvements on the CAPI side to remove the borrowed references, but also as maintainers of extensions, you can help if you actually adopt these new APIs. And also if you don't access like all the implementation details, it's always better if the implementation details are hidden so that they can be optimized away. And also regarding free threading, we should think early about how it's going to interact with optimizations with JIT compilation so that we don't end up with something that would be too restrictive and too detrimental to performance. And that's it from me. Thank you. From us.
Thank you. Thank you, Stepan and Michael. So we don't have the time for a Q&A session. So in case of any questions, I think you can find the guys somewhere around the conference and ask the questions directly.